we continue where we left in the last class. We started learning about strain gauges and their applications. Right. So we learned that the gauge resistance is R0 into 1 plus gauge factor into epsilon, and we also learned that today if you talk about a strain gauge, it is a bonded type strain gauge made of metallic film type, right? And each strain gauge has an axis in which it can sense. The axis that is 90 degrees to this is known as the quadrature axis or cross axis. Ideally, a strain gauge is not required, is not expected to respond to strain in the quadrature axis, but practical strain gauges will have a small cross axis sensitivity. So if in the main axis the sensitivity is 100, then cross axis may be 1 or 0.5, like that. So normally the cross axis sensitivity is given in terms of the main axis sensitivity, saying that cross axis sensitivity is 1% of the main axis sensitivity. So if you do not want to have a strain gauge which has a cross axis sensitivity, you must look at this particular specification when you choose, right? And we also learned that a strain gauge can be used in a bridge. So if I have one active strain gauge, we call this as a quarter bridge. So if this is EB, the output E0 we have already derived, EB by 4 into delta by 1 plus delta by 2, where delta equal to gauge factor into epsilon, right? So the we can also use two strain gauges, one decreasing, the other one is increasing. This is EB. So now E0 here would be EB by 2 into delta. Please remember delta by 2. The denominator 1 plus delta by 2 goes away. You get a linear output, and of course we can have all four strain gauges. So this is increasing, this is increasing, this is decreasing, this is decreasing, and the output E0 is equal to EB into delta. Get 4 times. So either half a bridge or full bridge also gives you temperature compensation, whereas if you have only quarter bridge, you need to provide temperature compensation. And when it's a quarter bridge, right, single active strain gauge, single active strain gauge you have to linearize the output, linearize the bridge output. There are two methods. One is single op amp, so we put EB here, and this this is R0 into 1 plus delta, this is R0, this is R0, this is R0, and E0 would be minus EB by 2 into delta. So this normally requires an amplification, so you put one more inverting amplifier. Okay. So this is R1, R2, output E01 is equal to R2 by R1 into EB by 2 into delta. Right? So we get a linear output, also amplified. There is also another linearization circuit. We call that as feedback linearization. So we have the usual bridge with one active strain gauge, RG, this is R0, R0, R0. We take this to output, take a part of that output, so this is beta times E0, R2, R1, this is grounded, then we have a summer here, so we give the bridge excitation voltage here, and the feedback is completed. So this we saw as A EB by 4 into delta, provided A beta equal to 2. Right? If I make beta into the amplification of the instrumentation amplifier equal to 2. We also looked at the instrumentation amplifier. The most popular one is the 3-op-amp instrumentation amplifier. The instrumentation amplifier has a finite gain. Gain is determined by just one resistor. Right? Let me draw that. It doesn't take much time. So this is E1 minus this is plus, again this is minus, this is plus. Oh, I made a mistake here. This is okay. So all are R. This alone is RA, and E0 here would be E2 minus E1 into 1 plus 2 RA by R. So by changing the RA, whatever gain you want, you can get the gain. As I already said, this is available in integrated circuit form, EE6403, INA 101. These are some popular instrumentation amplifier ICs that you can buy. Not that expensive at all. Then we learned that we can use the strain gauge and measure force, also known as load, then measure pressure. Right? So strain gauge of pressure sensors normally use diaphragm, diaphragm type of pressure transducers. So on the diaphragm, the strain gauges are fixed, and the output from the strain gauge would be proportional to the pressure difference across the diaphragm. So apart from this, there are other applications for strain gauges. We will see when we talk about transducers with mechanical input or physical input as the criteria, right? And this is where we stopped yesterday. Oh no, we load cell. There are two. Normally, the load cell can be classified into three: compression type load cell. Second is tension type load cell. Three is bending type load cell. Compression load cell, if this is the load cell, you compress, put the force down, so the structure gets compressed. So this is kept in a, right? Or you can also use differential compression. You put one on top, one at the bottom. Then also you get compression. Of course, this is compression. Single, differential. Then you have the same load cell. You pull it apart, tension, right? Put the structure under tension. This again can be, this can be grounded, and only single or differential can be done. Of course, bending we already saw. So we have a cantilever, and we put the force here, and this bends and hence creates a strain. So you put one on top, one at the bottom. Top one will give you positive strain, the bottom one will give you a compressive strain. So you get both compression and tension here. So apart from this, based on the structure, we have the beam or cantilever type load cell. So here you have a single beam. You also have double beam. Single beam is something like this. The double beam, of course, what you do is you put the put here, so it will bend like this. Then you have 1, 2, 3, 4, right, on both sides. Normally, double cantilever or double beam load cells are used for very large loads. For example, you would have seen lorry weighing machines where they weigh 30 tons, 40 tons, right? The load cell used in such applications will be invariably double beam, because it gives you a lot of overload factor, right? Apart from the beam, we have a button or mushroom type load cell. So you have the structure is something like this, right? So you apply a force here, and you put the strain gauges here. All of the normally either full bridge or at least half a bridge. We never use quarter bridge when it comes to load cells. 99.9% of the time we use full bridge with 4 active strain gauges on a load cell. The other type of load cell is the ring type load cell. So this is also known as washer type load cell, because a ring like this with a hollow inside looks like a washer, so you can put it as a washer type load cell. So either you can use compressive force or tensile force. It will work both ways. Again, what we do is we put strain gauge here, strain gauge here, 1, 2, 3, 4. Again, 1, 2, 3, 4. So there will be 4 strain gauges connected in a bridge form. So again, this can be, right, or it can even be kept on a hook, right? One side application only, that is also possible. The last S type load cell. So what you do is you make this structure and apply a force here. This again you can put compressive force or tensile force. It will work nicely. This is also very popular because this has a very good sensitivity. So if you want to measure micrograms, you normally use an S-type load cell. Okay. Okay, that's of course I am only giving like this. It will be three-dimensional, right? So we talked about load cells. The next resistive transducer that we are going to learn is known as the resistive temperature device. So simply called RTD. We all know if I take a resistor and expose it to temperature, let's say theta degree centigrade, the resistance with respect to temperature can be written as R naught into 1 plus alpha theta plus beta theta square plus gamma theta cube and so on. It will be really nonlinear because temperature effect due to temperature, the electrons go through a Brownian motion. They go all around the place, and then the resistivity increases. Right? Most of the RTDs are positive temperature coefficient, where alpha is positive. There are few RTDs which, in a specified region, have negative temperature coefficient. That is when you increase temperature, the number of free electrons increases, so you get decreased resistance, right? Only for a small region, otherwise it will always be. And the nice thing is that we should choose material which has beta gamma very small, and this is as good as possible, right? At least I'll say appreciable. So if you go through the literature in the last few decades or even last century, there are a lot of materials that have been tried, but today the most popular material is platinum, pure platinum wire, right? So the platinum wire with a nominal value of 100 ohms is called PT100, right? And the temperature coefficient is 0.0039 is the alpha. Beta gamma are really very small. So if I look at the 0 degree centigrade to roughly about 600 degree centigrade, I have R theta, right? Oh, this is not correct. So we have to have a at 0 100 degree centigrade, right? So 0 will be 100. A very linear, nearly linear characteristics, and the I don't know why this keeps coming again and again. Okay, sometimes the computer behaves very crazily. Anyway, let's see. That's the you also have PT 1000 and PT 10,000. Okay. So this is R naught is 100 ohms, R naught is 1000 ohms, R naught is 10K. These two are not very popular. This is very, very popular. So RTD is a temperature sensor. So I have the resistance varying with respect to temperature, where R theta is equal to R naught, where R naught is the resistance at 0 degree centigrade, 1 plus alpha theta, where alpha is the temperature coefficient, right? And unlike the strain gauge, if I am measuring temperature, it's only one variable resistance, so I can either use it in the bridge as single active sensor. So this is R theta, and this is R naught, R naught, R naught. So I'll get E naught here. So E naught is equal to, if this is EB by 4 into alpha theta by 1 plus alpha theta by 2. Right? I mean, earlier we had Rg equal to R naught into 1 plus gauge factor into epsilon. Now it is going to be 1 plus alpha into theta. Right? So we this is very standard temperature sensor in the industry, used in the industry, and you get to have a two terminal, right? So you have the sensor here, element here, and you have two terminals here. So what happens is, if I put a large resistance, then here there would be wire resistance. So red is RW. Please remember, whenever you want to measure temperature, the sensor must be sensing the temperature. For example, if you are going to sense the temperature of a heating element, you put the sensor on the heating element, but you can't put the electronics there because it will be lot of temperature there. So you'll have to put electronics away, maybe half a meter, 1 meter, whatever it is, even 10-20 centimeters. So there would be a wire resistance. So sometimes you have the three wire, right? So that these two can be used to compensate for the long wire. So you have 3 wire or 4 wire configuration. So it depends upon what temperature you are going to measure. If you are going to measure, let's say, only 100 degrees centigrade, you don't need a 3 wire configuration. 2 wires are good enough. But if you are going to measure something like 600 degrees centigrade, you really don't want your electronics anywhere near 600 degrees centigrade. You want it to be as much away as possible. So you may put 1 or 2 meters of wire. Then the guard wire, this is known as the guard wire, becomes essential. Okay. Another way that is popular, we already saw this in strain gauge. It's not popular in strain gauge, but popular, right? So you put cos theta here and put R naught here and put a current mirror and use an instrumentation amplifier. Right? We can also use the two linearizing circuits. Right? It's the same circuit, but instead of a strain gauge, now we put R theta equal to R naught into 1 plus alpha theta. R naught, R naught, R naught, and we put EB. So output we already saw, EB by 2 into delta, and we need one more amplification. Okay. So this will be E01, E01 is equal to R2 by R1 into EB by 2 into delta. Okay, so we can get a nice linear characteristics. The one advantage of PT100 or PT1000 is that it's quite accurate when it comes to measurement of temperature, and because of that it is also used as laboratory standard. Now, what do you mean by laboratory standard? Let's assume that you are measuring, right? Put a voltmeter and you are measuring voltage across 2 points in a circuit, and you measure 1 volt. How do you know that what it measuring is 1 volt or 1 volt? Of course, what you do is you take this instrument and calibrate. Right? So, how do we calibrate? Calibration can be done using absolute method. Second is comparison method. Let's assume that I want to calibrate a thermometer. What I can do is I can put the thermometer, right, in a tub, put with pure water and ice in equal proportion, right? So what happens is when water and ice exist at sea level, then this becomes exactly 0 degree centigrade. This is called triple point of water. So now I can put my thermometer and make that thermometer reach 0. The other thing is I can put water, pure water, and boil, right? I put a heater and boil, and when it is boiling, I know water boils at 100 degrees centigrade, pure water boils at 100 degrees centigrade at sea level, right? So I can calibrate the thermometer using these 2 points, make the thermometer read 0 here, and adjust the thermometer so that it reads 0. But many times that may not be possible. So what we do is we have a standard sensor and an unknown sensor, and we give the same input to both, right? So now whatever is the reading of unknown sensor, I call the unknown sensor reads X, that's a measured value. Standard sensor reads S, divided by S into 100 would be the error in X, right, percentage. So this is quite popular. Here what we are doing is we are finding out the error in X by comparing it with a standard. Now, what does standard mean? Standard must have error much less than X. Standard is supposed to be error free, but we all know it's impossible to make a measurement without errors. So only thing is if you are calibrating a 1% accuracy transducer, then your standard has to be at least 0.1% accuracy or 0.05% accuracy, so that this is sort of valid, right? So when we look at this standard, the standard has what is known as international standard, normally designated System International Laboratories, right? Then we have national standard, right? Our national standard is kept by National Physical Laboratories, New Delhi, right? And you have regional standard. They are also known as laboratory standard. The international standard has to be very accurate, maybe 0.004% or 0.0001%. National standards will be slightly less than that, and regional standards will be much less than that. So maybe 0.1, 0.01 can go as laboratory or regional standards. For temperature calibration, the PT100 and PT1000 or can be used as a laboratory standard. That's what when I said that the PT100 is used as a laboratory standard, that's what I meant. With respect to PT100, you can calibrate all other temperature sensors, right? In fact, there are very few transducers that qualify for this, becoming a laboratory standard, and PT100 is one of them. Okay. Now we talked about the potentiometric displacement sensor, resistive. Then we looked at the strain gauge. Now we learned the resistive temperature device, RTD, or sometimes also known as resistance thermometer, quite popular and quite accurate for industrial use and for calibration as well. Okay. Now we look at other types of resistive sensors. One is piezo resistive sensor. As the name indicates, if I put a resistive material here and apply pressure, the resistance varies, right? Piezo-resistive sensors were sort of very popular. In fact, it was one of the very first transducer that was made in very large numbers, right? If you look at telephony, you have a mouthpiece. We call this microphone now. The original mouthpiece that Marconi used was made like this, so he put resistive powder here and took one terminal here and one terminal here. So when you speak, the sound waves will vibrate this diaphragm, and that would adjust the powder density between the back side of the cup and the front side of the cup, and the resistance between these two will vary proportional to this pitch, right? So this is known as carbon microphone. Was used for several decades before the other types of microphones are invented. So this is actually a piezoresistive, because what is sound pressure? Sound waves, sound pressure level changes, and this converts the pressure change into resistance. So that is one piezoresistive sensor. Today, piezoresistivity is used in what is known as micro electromechanical systems. Other than that, there are not very many commercial applications. But there are some applications where you use the piezo resistivity again in the same, right? So you have a, this is an insulator plastic, this top is a bubble, again you put carbon fiber, you apply a force, this will bend and change, resistance will change. So you take two terminals across this, so across this you have a change in resistance which is proportional to the pressure applied. This is a very popular sensor used in robotics because you can use this as a touch sensor on the robotic fingers, and hence get an output. The nice thing is, even if applying very large pressure, nothing will happen. It will just come and rest at a particular level. So the overload factor of this type of piezoresistive bubble sensor is really, really large. You can make it to sense very small pressures, at the same time handle large over pressures, which is many times required when you are dealing with robotic arm. Okay, so that's the piezo resistive sensor. There is also a light dependent resistor. You take a semiconductor, and you put light, the resistance will change with respect to light, right? Okay, this was very popular quite a while ago, and this was one of the photo sensor, because if you want to convert light into an equivalent voltage, you need this. In many old film time cameras, you would have a light meter, so you measure the light and adjust the camera parameters to suit the ambient light, and invariably you see an LDR, light dependent resistor inside. Today they are not very popular because if I look at intensity versus change in resistance, it is an exponential curve. And this is normally silicon or some kind of semiconductor. People even used compound semiconductors to make LDRs. Then the last of the resistive transducers that we are going to learn is called thermistor. Thermistor is again just a blob of semiconductor, right? Maybe a P type or an N type, it doesn't matter, right? And if I put temperature on the semiconductor, what happens is inside the semiconductor you have nucleus and free electrons. If I put thermal energy theta, the energy given to the free electrons increases, so I have the number of electrons becoming higher, so the resistance will drop. So again, if we look at the resistance of a thermistor, it is highly nonlinear, right? And also normally a semiconductor will work maybe minus 50 degrees centigrade to about 150 degrees centigrade. That range is also limited, but nevertheless this is very, very popular as a temperature sensor, especially if your range is very small. For example, you want to measure ambient temperature, the range would be about 10-20 degrees centigrade. Similarly, if you want to measure the body temperature, it may vary from 34 to 40 degrees or 41 degree centigrade. So what we do is, if this is the, I expand this, if this is the exponential characteristics, so if this is my range, within the range I linearize it. I say that it's linear, right? So we call this as piecewise linear. Right? One small range we take. Many times when we want to measure a living temperature for living thing, maybe animal, maybe human, this is very good because sensitivity is very high, right? I will give you the data in the next class. Sensitivity is really very high. 100 times more sensitive than the resistive temperature device. Uh, so it's very easy to use it in a very limited range. In the limited range, you can linearize it and use it as a sensor. And the second advantage of a thermistor is that it is inert. For example, if you take platinum, platinum reacts with water, it reacts with acid, so it's not inert, right? So if you want to use a platinum resistance thermometer, you have to encapsulate the platinum wire. Normally a small platinum wire is encapsulated in a bulb, right? And this could be made of glass, right, so that it is insulated, or sometimes even highly insulating fibers are used. But whatever it is, it has to be protected, right, because it needs to be protected. Okay, and the moment I put glass, and if I put a theta and I increase the theta in a step fashion, the theta actually here, theta sensor would slowly rise and go to normally this is few seconds, right, 10 seconds, 20 seconds. That's because we have to protect the PT100 with a glass. So the dynamic response of RTD is quite bad. On the other hand, if I look at thermistor, I don't need to protect it. What is thermistor made it of? Silicon. And what is silicon? Naturally occurring material, and it doesn't react with anything, right? Uh, so because of that, we also call the thermistors as biocompatible. So whenever you want to get a biocompatible temperature measurement in a small range, not because they are not useful for large ranges, you can use thermistor. You can also use thermistor, but again not very popular. You can linearize the exponentially decreasing characteristics. Most of the thermistors have resistance decreasing with respect to theta. There are, we call this as negative temperature NTC thermistor. There are few thermistors where the R theta is increasing. So the characteristic will be something like this. Again, nonlinear, exponential, all those you cannot avoid. But these are very few. Positive temperature coefficient resistors are not that popular, mainly because you have to do a lot of trick to get a PTC type of thermistor, whereas NTC type of thermistors is quite normal, and you don't really need to do anything, right? And there's also something called resistive Bolo meters. So these are again resistances which can absorb radiation at certain levels, and the resistance will change, right? This is again a very niche sensor, not that popular, right? Um, uh, in the past, bolometers were used when other sensors were not there. Today we have better sensors. We learn them as we go by. Similarly, if I look at the uh, LDR, today LDR is not at all used, mainly because we have what is known as photodiodes and phototransistors that are quite good compared to in response in terms of time response as well as sensitivity, much better than LDR, and also in size. LDR, you need a certain area for the resistance to come under influence of temperature or light and change, right? And whereas photodiode or a phototransistor, all you need is maybe 10 micrometer by 10 micrometer area would sense both light and heat very nicely if you use a photodiode or a phototransistor. Okay, so I uh, stop here. We will start learning about inductive sensors next week. Okay, so most probably I will also upload the first assignment next week. Uh, you will get sufficient time to uh, solve the assignment. Okay. Okay. See you in the next class.